How do companies like Netflix, Amazon, or Spotify instantly recommend content to millions of active users without slowing down their website? The answer is scale separating heavy machine learning training in cloud from sub-millisecond serving at the user end. Welcome back. In this video, I will show you how I built HelixRec, an enterprise-grade hybrid recommender engine using Databricks, Spark, collaborative filtering, and TF-IDF. It processes over 100,000 movie rating in the cloud, blend multiple recommendation strategies, and serve results through a fast SQL layer into an interactive Streamlit dashboard. Best of all, the entire pipeline is fully cloud hosted on Databricks Unity Catalog volume. Let's dive in.
Never run models live. That's too slow. Databricks computes batches. Unity Catalog stores them. SQLite serves them instantly. Streamlit renders it all.
Let's talk about the libraries that make this possible. PySpark, SQL, and ML library, the backbone of our big data engine. We use Spark data frames for distributed data processing, Spark ALS, alternating least squares, matrix factorization for collaborative filtering. PySpark NLP feature, we use tokenizers, hashtagging TF, and IDF pipeline to perform natural language processing on movie, genres, and user tags. NumPy, so used to run a custom high-speed vectorized matrix multiplication on the driver node to compute cosine similarities. SQLite and SQLAlchemy, our local caching database layer, it translates our Spark exports into indexed relation database tables. SQLite and Plotly, our serving frontend. Streamlit creates our UI elements and Plotly renders our interactive charts. We start by importing our Spark ML and SQL modules and setting up our Spark session. Databricks automatically manages the cluster session, but we declare it explicitly here to ensure cross-environment compatibility. Next, we download the movie lens dataset. Notice the part. By writing that directly to this volume, we comply with strict Unity Catalog cluster security policies and avoid any permission errors on shared cloud instances. Here we load our CSV files into structured Spark data frame because Spark uses lazy evaluation. It doesn't read the data until we call count. This is the heart of collaborative filtering. We use ALS to decompose our sprays user items and interaction matrix into low-ranked user and movie factors. To find the optional hyperparameters, we use a threefold cross-validation grid search. We set cold start storage equal to drop to handle users not seen during training. Once the model is trained, we evaluate its rating prediction. Our best model achieves a test RMSE of approximately 0.8240, which is a highly competitive rating prediction accuracy. Collaborative filtering is great, but it fails for new items. To solve this, we extract content features. We group all user-applied tags and genres for each movie into single text block and run a Spark NLP pipeline. This converts every movie into normalized TF-IDF vector, representing its characteristic. Finally, doing a Spark self-join with a Python UDF to compute concise similarity for 47 million pair takes over 30 minutes. Due to JVM to Python serialization lag, to optimize this, I wrote a vectorized NumPy method. We collect the vectors to the driver node, run a single node matrix multiplication in NumPy, filter to the 20 similar items, and convert it back into Spark. It goes from 30 minutes to under 3 seconds. Now we blend them. We calculate the hybrid score by combining 60% of ALS rating prediction with 40% of content similarity score. If a movie is both highly rated by similar user and shared tags, with movie the user linked, it traces to top of our recommendation list. To verify our ranking quality, we evaluate the model against actual user rating on the test set. Our hybrid recommender achieves a 18% improvement in map and a 17% improvement in NDCG20 compared to collaborative baseline alone. We coalesce and write our output table as clean CSV file back to our volume exports directory, so they are ready for serving layer. We import the CSV from the volume into our local SQLite database. This creates our schema, populates our table, and indexes them from sub-millisecond query retrieval. And finally, we run our Streamlit server because we are in the cloud. We run the server in the background and construct a secure Databricks driver proxy URL to bypass cluster firewall. User recommendation tab. When we query user, we immediately see they have rated 100 movies with a perfect 5.0 average. On the right, we see the top 10 recommended movies with the score broken down into the ALS collaborative score and the content score. Cold Start Simulator tab. It is the new user searches for Anaconda. The app queries our TF-IDF cosine similarity matrix and immediately recommended Con Air, Mission Impossible, and Cliffhanger, showing how we successfully handle new user. And the system performance. Here we visualize our ALS hyperparameter tuning curves and compare our map and NDCG metrics, showing the clear superiority of our hybrid blender. And that's it, HelixRec, a complete enterprise-ready hybrid recommender system running on Databricks cloud hosting. All source code is committed and pushed away on my GitHub. If you enjoyed this video, hit the like button and subscribe. See you in the next project.